Okay, thank you, Francesco, for your words. Of course, I would not take the thing that he said too seriously, but I mean, we try to sort of. First of all, let me join the words of appreciation that Antonio made about the thought of Francesco of gathering people from different with different scientific interests in this nice place. I'm going to talk about this nice problem of bubble collapse, and I'm glad to say that I learned some basics about this problem actually in this room a few years ago when Pierre Sepecher was asked to give a seminar on second gradient continua and fluids in particular. So we get interested a lot on this kind of description, and we try to use these things to do some fluid mechanics. First, let me try to introduce the framework in which cavitation problems are of interest. Cavitation has a huge range of physical and technological situations in which it is of paramount importance. Here you see a few pictures concerning damage on the structure associated with the implosion of cavitation bubbles near a solid surface. That one is a Francis turbine, an hydraulic turbine, which is almost completely destroyed by this effect. During the bubble collapse, enormous temperature and pressures are reached. There are significant conversion of thermodynamic energy into kinetic energy of the fluid, formation of shocks into the fluid that altogether lead to this kind of effect. Perhaps one of the nicest ways to visualize cavitation is looking at the ship propeller, in which you see the formation of these bubbles in the low pressure region associated with the tip vortices of the blades. But there are also applications or interests at different scales, for instance at the micron or even nanoscales. And on the left side of this slide you see that there are several interesting applications in medicine. For instance, you can use cavitation for extravasation of drug across the walls of a blood vessel. So you induce the formation of the cavitation bubble by ultrasounds. The bubble forms, then starts oscillating, then at the end collapses, and in collapsing it forms a jet, and this jet is able to open a way across the endothelial cells, opening a passage from the interior of the blood vessel to the tissues that are surrounding the region. At an even smaller scale, cavitation may be employed to do the same kind of effect, opening a small passages across the cellular membranes. This effect is called sonoporation, and there are interesting applications of drug delivery dedicated to direct cellular delivery of drugs. Concerning me as a fluid mechanicist, I think that the sketch of the overall phenomenon can be illustrated like this. You have a duct in which a fluid, a liquid is flowing, for instance water, then there is a contraction, and this leads to a depression associated with the Bernoulli equation. Since typically water transports some kind of dust particles, they act as cavitation nuclei, so when the pressure falls below a certain level, this nuclei grows, they form bubbles, which are successfully reabsorbed in the region where the pressure increases again. As you see, this problem is a rather tough one, in the sense that it involves a huge range of different length scales, from the macroscopic length scale of the fluid dynamic device down to the microscopic or even nanoscopic dimension needed to address the nucleation of these bubbles. In principle, I mean, the different phases of this process can split up in several steps, and there I was indicated 3 of them. But of course, going into detail, there could be even more subtle distinction between different aspects of this kind of problem. Here is an example of what we are looking for. That is trying to set up a simulation in which you have a vapor bubble. You see here the density field, so the blue is low density corresponding to vapor. The red part is related to high density, that is the liquid. A shock wave is propagating through the liquid and generates the collapse of the bubble. On the left side of the slide, you see the contours of the gradient of the pressure that allows you to visualize in a better way the interfaces which are formed during these events. So you see the interface between the liquid and the bubble and the shock wave propagating through it. At a certain point, due to the presence of a solid wall at the bottom, the symmetry of the process is destroyed, and you deform, the bubble is collapsing, forming a jet. This jet is going to interact, this downward flow induced by the jetting generated with the deformation of the bubble, is going to interact with the shock wave which is going to be reflected from the wall, and you see here a strong shock wave forming in front of it. This is what is called water hammer. This water hammer is able to increase the pressure a lot and also increase the temperature. This is one of the reasons why the solid material with which the surface is built is going to be destroyed by this event, because you are going to have this shock wave impinging on the surface together with this excavating flow of kinetic energy which is going to impinge on the wall. So this is just a picture to illustrate the overall picture. At the present moment, this picture is not a scientific result. It's just preliminary computation. I'm going to talk about a little bit more details of something that we can control with more detail. Okay, again, before entering into the detail, I want to show you some experimental visualization of the process. This is a picture taken from a paper of Hall and co-workers, in which, using high-speed cameras, they are able to visualize the process of bubble oscillation, collapse, and shock formation. So you see that the bubble is shrinking, and at a certain moment, this shrinkage of the bubble stops. The bubble rebounds and starts to expanding again, and in this condition, a shock wave emerges from the bubble and is propagated backwards into the liquid. This is the kind of problem that we would like to address in some more detail in the following. The classical way to approach the problem is through what is called the Rayleigh-Presset equation, the Rayleigh problem, which is a one-dimensional equation which is obtained by integrating the Navier-Stokes equation from the surface of the bubble towards infinity in the direction of the liquid. You do some integration and you end up with a nonlinear equation for the evolution of the radius of the bubble. You can solve it and find some interesting results. For instance, in this case, what you see is the behavior of the pressure pulse, which is propagating away from the bubble once the shrinkage of the bubble has been stopped. Okay, now some literature. We would like to address the problem using a class, a specific technique taken from a class of methods which are called diffuse interface method, and which starts from a seminal paper from van der Waals, who was the first to address capillary flow as a continuous distribution of density, a sharp variation of density which was assumed by him to be continuous rather than discontinuous as Laplace was taking it. There have been also, in a slightly different context, interesting, important basic contribution from Kahn and Hilliard, who derived a sort of model which is related to in a generic sense, to this van der Waals one, for describing the behavior of immiscible fluids, for instance. For those who are interested in fluid mechanics, there is this nice review in the annual review of fluid mechanics by Anderson and McFadden who sort of describe the basic contribution done by using diffuse interface methods in the field of fluid mechanics. Now, here are more recent contributions from some friends of ours. So, I mean, there is no claim of generality. These are a few nice papers that I wanted to explicitly cite in this audience. And I think the first one is a very interesting paper, and it's one of those who inspired us in trying to follow this kind of approach to look for this extreme solution in which you have shock wave propagating in the system. Okay, so I won't enter into the theory in much detail. The generic framework is related to this second gradient materials, second gradient fluids. Classically, I mean, theoretically, the way to start the thing is assuming a Lagrangian point of view following material particles along the deformation. But in fluid mechanics, we are much more happy with an Eulerian point of view. That is, we attach a field to every point in space and time. From that point of view, everything starts from defining a free energy functional, which is a functional of the density field, of the velocity field, and of the temperature field, in which you have the kinetic energy density, the free energy, thermodynamic free energy of the bulk phase involved in the problem, and then there is a sort of penalty associated with the formation of the gradients. So the term with the square of the gradient of the density will originate the capillary stress, which corresponds to surface tension in a more classical sharp interface description of the problem. In the simulation I'm going to show you, the bulk free energy is assumed to obey the van der Waals equation of state. This is because we want to have a simple model, but one able to describe phase changes into the system. So we will have a transformation from vapor to liquid and backwards, and this should be embedded into the simulation. From the free energy functional, you can extract the chemical potential as the distributional derivative of the functional, as well as the entropy density, which is related to the derivative with respect to the temperature field. And then we have to do something more. I mean, if you stop everything at that level, you will have what is essentially an Hamiltonian system. You will have a Lagrangian description, and you can recast everything in terms of Hamiltonian equation for the field, so the system is conservative. And of course, in this case, when you have viscosity, you have shock waves, you have heat conduction, a Hamiltonian system is not enough, so we have to add on additional effects. And this is done completing the stress tensor with the part which are related with diffusion, so with the constitutive equation for a Newtonian fluid. Then we will have an energy flux, which will have the classical contribution due to the Fourier law of conduction, which is to which we have to add the contribution arising from the density gradient and the velocity divergence. And of course, what we claim is that the whole system should satisfy a Clausius-Duhem type inequality for the entropy density. So one can more or less easily derive an evolution equation for the entropy, in which you have the entropy flux, defined as the energy flux divided by the temperature, and on the right-hand side, you will have an entropy production term, which is explicitly reported in the bottom line. Of course, the claim is that this production term should be positive definite and will be zero only in thermodynamic equilibrium conditions. And this enforces some limitation on the kind of constitutive law that you can postulate for the dissipative contribution to the stress and for the heat conduction term. The two constitutive equations that I'm showing, of course, satisfy this Clausius-Duhem inequality, so we are happy with the overall result, and we have a system of equations that we can solve, which reads like that. So overall, what we have is mass conservation, which is an equation for the density field, momentum balance for the velocity of the fluid. On the right-hand side, you have the divergence of the stress, which has extra contribution associated to the distributed capillarity in the field, which are highlighted in red here in this part. And then there will be thermodynamic prescription concerning the dependence of the internal energy on temperature, on the presence of an extra energy, the interfacial energy associated with the interface forming within the vapor and the liquid. And then from the van der Waals equation of state, we get the classical equation relating the pressure in the homogeneous bulk phases to temperature and density. Okay, the system is not a strictly standard one. There are some crucial aspects that have to be addressed before one can attempt a solution of the problem. The first observation to be made is that the interface between liquid and vapor can be even considered to be a smooth one, but of course the thickness of the interface is extremely small. This means that you need a very huge resolution in order to capture the behavior of the fields across the interface. A second point is that the van der Waals equation of state describes a compressible fluid, meaning the vapor, which is of course compressible, but even the liquid, which has its own compressibility. Although the compressibility of the liquid is a small one, of course, there are shock waves propagating also in the liquid, and the sound speed in the liquid is much higher than in the vapor phase. So that you have shock fronts propagating in a non-uniform multi-phase environment. So your numerical algorithm should be able to cope with this kind of difficulty. Then there is a third point that I would like to highlight. This, from the mathematical point of view, the system is I called it a compound one, in the sense that there are different physical effects described by the operators involved. And one is the fact that you have acoustic propagation, either acoustic wave or shock waves in the extreme cases. And this induces a kernel which behaves in a strongly hyperbolic way. In other regions of the field, however, there are other effects that enter into play, introduced by viscosity and capillarity effects, and these are typically not hyperbolic. So there are regions with strong hyperbolicity related to the region in which you have capillarity and viscosity. More than that, if you look at the phase diagram of a van der Waals fluid, you discover that almost everywhere in the phase diagram, the sound speed is a well-defined physical quantity. The sound speed, the square of it, is defined as the derivative of the pressure with respect to density at constant entropy, and this C-square should be greater than 0, of course. And this happens almost everywhere. There are, however, regions below the spinodal line where this prescription is not true. So, in what is called the coexistence region, if you take this derivative, the C-square becomes less than 0. So there locally, you can no more appeal to hyperbolic evolution of the system. From the practical point of view, this leads to the failure of standard hyperbolic solvers used in gas dynamics. I have to speed up a lot. Okay, so a few keywords concerning numerics, which I'm going to skip unless somebody is directly interested on that. Then the physical system is a nano-bubble, and we take the bubble in equilibrium with the liquid, we increase the pressure in the liquid, overpressure, the bubble starts shrinking. What happens is shown more or less clearly here, in which you see the pressure. You see that as soon as the system is released, the bubble starts collapsing, and in the meanwhile, you see an expansion wave propagating in the liquid. That is, the liquid is going to recover its equilibrium pressure. It was overpressurized, and once the bubble moves, an expansion wave emerges from the bubble and goes into the liquid. Then the interface starts moving faster and faster, and this is going to compress the inner part of the vapor bubble. And let's see what will happen. So this was a rather clumsy slide concerning what we know about shock waves in a van der Waals fluid. I will skip all these details. I mean, these are known from the paper by Zhao et al., for instance. And this is a picture of the field that you have. So you see the bubble who is going to shrink, and at a certain point, the shrinkage of the bubble stops, and the radial shock wave is emerging into the liquid. This is the time behavior of the radius of a bubble. I think this is an extremely interesting result. I was a student to teach a class. This is an extremely interesting result in which you see the effect of the overpressure, different curves correspond to different overpressure in the liquid, and the effect of thermal conductivity. Once you have this bubble collapsing, the pressure and temperature inside the bubble increases a lot, so that you will have thermal losses to the liquid. This is going to slow down the effect inside. And what you see is the behavior of the bubbles for different overpressure and thermal conductivities. The interesting point is that you see that the bubble is rebounding. It bounces back. It collapses, then it expands, and it collapses. This kind of behavior is highly unexpected, in the sense that it is well known for incondensable gas bubbles. The incondensable gas is compressed. It stops the collapse and expands, not for vapor bubbles which are expected to undergo a phase transition to the liquid. Okay? Why these kind of things happen? The reason is that during the phase of shrinking of the bubble, you are going to have a compression of the vapor phase and a release of latent heat of condensation. Okay? If the energy lost over the liquid is not fast enough, this is going to increase pressure and temperature inside the vapor bubble, which undergoes a transition to supercritical fluid, becoming a sort of high density incondensable phase. This is why at the center point the bubble stops shrinking and expands back again, and it can do this several times. And each time that the process is reverted, the bubble shrinks, expands, shrinks again, and every time the shrinking is stopped, a shock wave is emitted into the liquid. There are a few details that I don't think I have time to discuss now. How many seconds I have? Outside. So, yes, this is a compound phase diagram in which we are trying to track the different phases of the system, vapor, liquid, etc. And, well, I think I have to stop here by recalling that by using this second gradient theory for this vapor bubble, we have extracted a few, we think, interesting items of physical understanding. For instance, we understood a little bit more clearly how the shock wave is forming. I mean, the bubble is going to shrink. At a certain point, it reaches the sound speed. At that point, you have a strong focusing of the pressure wave inside the bubble, which turns into a focused shock wave shrinking down. Okay? At a certain point, this shock wave is reflected back and emerges from the bubble interface toward the liquid. This effect is important for cavitation because it's going to lead the synchronization of the collapse of the bubble nearby. You have a bubble which is collapsing, it sends out a shock wave which triggers the collapse of all the guys which are nearby. There are a lot of important issues, technical issues concerning the numerical modeling, because you have to appeal to rather specialized techniques to solve this problem, because I said the problem is rather composite in its mathematical nature. And, well, I think I have to stop here just by recalling some cooperators that worked with me on this topic, and people who supported us from the economic point of view. Okay, thank you.
Question. everybody wants to have a coffee break, I think.
I think
with comments.
I think
in 90.
I think there's one there.
Ah, there is one.
Here.
Go ahead.
If I don't understood, there is a region where bubbles become surface resonators, and then it leads to the bubbles. And if a wave has a small amplitude, then they have a region that they don't collapse, but just respect and absorb the energy, and we have a particular propagation.
No, that is possible. Clearly, there are regions in the phase space. I mean thermodynamic condition, dimension of the bubble, frequency and amplitude of the incoming acoustic wave, which is forcing the oscillation, in which the bubble responds actually as an oscillator. This has a tremendous implication as concerning the acoustic propagation in bubbly media, because when you have this acoustic wave propagating, then these oscillators can work either in phase or out of phase with the incoming wave, and can lead to the depression of the acoustic emission across this bubble curtain. I'm aware. I mean, I've been told that these effects are used to shield sound emission for submarine, for instance. There can be cloud of bubbles that at least destroy the acoustic signal generated by the engines, by the propellers, so that from outside it becomes much more difficult to understand which kind of ship is going through. Yeah.